Shirley Clark is a professor of environmental engineering at Penn State Harrisburg. For those folks in the room, Shirley you might not see at University Park a lot because she's in Harrisburg and is part of the BSEC team. And James Hunter is, James, you're the head of your department, right? But do I remember interim being on your moniker? Something like that. Yeah, he's an associate professor in civil engineering at Morgan State University and is also part of the BSEC team. Shirley and Clark both study stormwater and are working with our group. So we thought it'd be interesting, urban stormwater. So we thought it'd be interesting to hear about their work today. There you go, Shirley, or okay, James, whoever wants to lead off.
I'm going to lead off. And then what we're going to do with this is I'm going to give a little bit of overall background and a little bit of the work we're doing in Middletown. And then James is going to finish it up with the work that he and his group are doing down here in Baltimore. So I titled on my part of the presentation, The Challenges of Historic Urban Land Development. That's really one of our big challenges in both Baltimore and much of the Atlantic. And again, I want to make sure I acknowledge my fellow researchers who are helping with that. You can see a long list right there. I will focus a little bit of this on my borough, Middletown, which is at the confluence of the Swatara Creek and the Susquehanna River. And I want you to understand that over time, you can begin to see that we just don't see the creeks anymore. A lot of this is actually buried. We built out, we've had different land type developments and all of this. So we're basically trying to figure out with all this different time zones, all this different land development types, housing, lot sizes, etc. In Middletown's case, we dug out and refilled canals. What is that impact on flooding? And what are we assuming? So again, we're actually, you know, when we really look at this, we're really looking at the issues around soils. And, you know, currently most good developers like to strip off the land, grade it. And what they're hoping for, let me see if I can switch this thing over. Oops, didn't mean to go that direction. Went in the wrong direction. Apparently I can't get the little thing to work. Anyway, so what we're hoping for is that we're going to get, you know, nice turf and we're going to get great infiltration and we're going to get this nice healthy soil. We end up with is a very compacted soil. And a lot of challenges from that. Now we do want a very compacted soil sitting under our buildings. So I really like the idea my building's not going to topple over. But the trick is with urban land development is trying to figure out where we want to have structural support from the soil and where we want to have infiltration. And that is something our land development practices haven't really led us to. So again, if I look at this coming up, I love this photo from Prince George's County. Here's a nice healthy soil, and you can see up in this top part how we really only have a healthy soil for a couple of inches. Down below this you know, light orange area, light brown area, really is almost acting like cement. And again, we're just not getting water in there. And we're assuming we're going to get deep infiltration of stormwater. We may not be getting that to happen. So we really have what I'm going to call the urban soil conundrum. We're trying to hope for that our urban soils are going to give us structural support. We're hoping it's going to give us water quantity treatment so that the water that's going to end up on the grassy areas is going to end up in the deep groundwater and not end up in our streams, in our streets, and in our piping systems. And one we're not going to talk about today is we're also hoping it's going to give us some water quality treatment. This is really important because, again, you look at the Chesapeake Bay watershed, just you know, just over 9.5% of the watershed is turf grass, basically your urban lawn. And in parts of Baltimore County and Virginia, often we'll see turf grass to be greater than 35% of the land area. When we think about development, they've stripped off the topsoil, put some back and thrown the grass on top. Lawns represent 70% of Pennsylvania's 2 million acres of turf grass. So again, we're really trying to figure out how we can deal with this and how do we really model this, because we're concerned it's causing and exacerbating our flooding. We are seeing more frequent of these high intensity storms. Again, one of our storms of record, Middletown, was Tropical Storm Lee, where we had about 13 to 14 inches over 4 days. But about 6 years later, we turned around and we had 4.71 inches in 87 minutes. There is no place you're going to put that water. But we're continuously coming in and having these high intensity storms happen more frequently. And they are causing many of our urban challenges with flooding. And so this is actually the 2017 storm. My grad student was very good. After the rain, he actually got out. That's actually somewhere in here, a creek that should be going underneath the state highway instead of over the state highway and running down along the railroad tracks and filling up our underpass down there. The underpass filled up so much that effectively it overtopped the underpass and flooded 3 streets down. I mean, so there's no place to put this, but the question we're going to have to ask is our land development practices making this worse? And again, what can we do about it at that point? So the very simple way, again, many of us on BSEC are modelers in different ways. We think about urban water flow modeling. I like this graph because effectively what it's saying is that we get some precipitation, we get some evapotranspiration, we do get infiltration. Some ends up in our sewer pipes, but hopefully most of it goes to our groundwater flow. And what we're not asking is what happens if there's a problem in the middle of this. And so my question is how does historic development affect what's happening now? What do we look at with this hydrologic cycle of urban systems, and how does the substantial modification of natural soils that occurred even before we had this big heavy machinery running on diesel, how does this actually impact what's going on? So again, my little borough, there are these old streams right here. There's one coming through here, one coming through there, one in here. None of them are above ground except for a little segment right here, and there's a little teeny piece right up there. Everything else is below ground. So what they've done is they've taken these natural water bodies, they've put them in a pipe, and again coming through, and then they've buried them. We also had in our area an old canal system and a mill race. And if we come along and look, note that, again, there's that mill race and that stream. And we'll come back in. Here's those maps overall. There's our creek. There's our old canals, our mill race, our log ponds. Note they're gone. Note they're really gone. So we dug this out. We tried to line these things so they don't leak. So we really tried to go in and put in clays or other material that would keep them from leaking. And then we turned around and decided that we're done. Railroads took over. And we tried to fill them back in with whatever we could find. We have found in these things oyster shells, because somebody in town liked to haul up oysters from the bay. We have found coal chips. We have found construction debris. We have found everything in there with a little bit of dirt thrown on top. And again, it's not a natural native soil. And of course, because of this, we're looking at unnatural flow patterns that could be affecting how these heavy, intense storms are infiltrating or not infiltrating. So we think about compaction. Again, we're really talking about the healthy soil. Is you would have the soil, you would have the water held by surface tension, and then you would have air. But we start talking about creating soils that we can put roads and buildings on. We're really trying to compact it. We are trying to make sure that it is as strong as we can get and then supplement it with any of our foundation work, which means that effectively we have reduced that porosity. We've really tried to take out that airspace and push it all together. And so again, that's what we end up having happen. You can see that the soil particles have gotten closer together, get a lot more water. The water's in there, there's very little air and there's very little movement. And what we see with that, back to that picture we had, is that if we come in and model this, this is basically a residential area looking at this piece of it. And what we end up seeing is that early on, we're going to get what we would expect. The bulk of the water is coming off of streets and sidewalks and parking and the roofing. All those things that are impervious, all those areas where we cannot put water in. But it doesn't take but a couple of inches of rain before, 18 to 20% of the runoff is actually coming from our lawns, from our landscape areas, park areas. And again, the more water we get, the more likely it is that those landscape areas are significant contributors. And we think about some of the models don't include that, including several. They're interesting down here in Maryland, where they calculate some of their volume based only on impervious area, your sidewalks, your roofs, your streets, your driveways. So these are the challenges we're dealing with. And so we've gone out, and this is some of it from the south, and we talk about infiltration and looking at modeling losses. But these were actually measured doing double ring infiltrometers, but also looking at whether the soil is compact or not compact. And very interestingly, for sandy soils, that saturation, wet versus dry, did not make a huge difference. What did make a difference was compact versus not compact in terms of the infiltration rates. And that's critically important because the equations that we're using in urban hydrology to model how much water infiltrates are a function of saturation. Compaction is not included. And so if we're not including compaction, we've got a challenge. Now, if we're in a clayier soil, They are both important, and really it's a combination of the two. In order to get a lot of water into a clay soil, we would need it to be both non-compact and fairly dry. So again, this is part of that challenge with modeling, though, is that compaction is not included. And again, I want to add to this the fact that there is a whole lot of infrastructure underground. And so again, how does this infrastructure impact our water flow paths? And again, what we're really trying to ask at this point is that, let's just say we have a pipe coming around and we actually have a stream buried in it, which is very common in Baltimore. It's very common in much of the East Coast. Again, particularly when they would throw pipe material on top of an open creek, and a lot of cases to get rid of the smell, because that's also where waste was disposed of. Some of it being sewage, some of it being just whatever household waste it was. So now we've got the stream flow. We've also got some shallow groundwater flow, because basically many of our older pipes are in very poor condition and they leak like a sieve. And then we've got, now what we're trying to do is see if we've got stormwater from existing development, and we add that on top of that, are we actually going to exceed that, particularly in these heavy, intense thunderstorms? And if we do, we get it out, and then we start looking at whether or not we have that flood. So what we're really trying to do is quantify the lateral shallow groundwater flow, thinking that water is not just going deep into the soil, but it also may be flowing laterally in the shallow subsurface, intersecting with our pipes and our trenches. So again, if that goes up and down, what space is available in our pipes for us to put stormwater? And then if we do that, do we actually predict the right amount? So the real question that this project is driving is, in the subsurface, which way does the water flow? Again, if we think about the blue arrow, the big blue arrow is the rain coming in, and it's going to go down by whatever layer until we hit this compaction layer, that layer where that bulldozer and that backhoe did a great job of compacting the soil. And then we came back in and threw something on top of it so we could put some grass seed down. How much water penetrates that and then can go down to the deeper groundwater, and how much moves laterally? What really we're asking is, what's the size of these two arrows? My mouse pad's a little sensitive over here. What's the size of those two arrows? And that's what we really need to understand in order to understand what's going on in the urban hydrology setting. And what we have in our houses, of course, just thinking about that, even our houses have a lot of utility lines. And you can see the different types of utility lines, and this is a very nice picture of what happens when you dig down. Now, at your house, this may be buried in soil, but it also could be buried in a trench filled with gravel. And again, if you've got a trench filled with gravel, suddenly you've got this compacted soil, and you've got this trench filled with gravel that may be going into your house and giving you an easy way for water to penetrate the house. So it's really trying to understand what's going on, because of course you really want your internet cable and your drinking water and your sewer lines to connect from the house to the street. So it's going through the yard somewhere. So there's just a lot of underground infrastructure that we don't understand how that impacts water flow. And part of what this project's going to do is allow us to begin to understand that. So we've been going out and doing measurements again with this, and this again, we're doing some double ring infiltrometer tests, some surface resistance measurements, as well as, again, this right here is a compaction meter. And all we're really looking to see is what's the depth of to the soil, where we hit about a 300 PSI or 2070 kilopascal resistance. Again, at that point, you really can't penetrate roots. We're not quite as firm of a soil as you would be for like a landfill liner, but we're getting pretty close. What we found is on many of our residential sites, it's highly variable. And you can see over here that it goes from 1.5 inches to just across our little back sidewalk to about 28 inches where their sewer pipe is. Again, you get a lot of leaking water. The soil gets a lot looser because it gets wet. So there's a lot going on. Even over here in the garden where they till the soil, you can get down to about 9.25 inches. Interestingly, when we also went in and looked at our local park, because here is that stream I mentioned earlier that's buried. And again, overall, what we found was that, again, the white ones are after several weeks of no rain, the blue ones after a decent sized rainstorm. And so what we see is that compaction layer actually moved down. So it went, for example, in this top corner from 2 inches below the ground surface to 5.5 inches. So it's actually not impermeable. So we have to label it as semi-permeable. So again, once it gets wet, it does transmit water. So now we need to understand that combination mechanism, because it's not impermeable, so it's not a dead stop, but it is a resistance layer. So we actually were confirming this at 2 sites in Middletown. One is in that park site you just saw, which is the bottom picture. If you look, you don't really see any change in color through here. It's a little bit harder to see up here, but this is the water treatment plant with the old mill race. You can see almost a red clay layer lens in there. And effectively, that is where they backfill back in for the mill race. Above that, again, the mill race, they tried to pack with clay so it didn't leak. They're trying to bring enough water down from the creek in order to run a 4-story grist mill. So what's interesting with these two is that these are responses to the same storm. And again, when I talk about the part top and bottom, or the water treatment plant top and bottom, one is above the compaction layer and the other one's below it. They're about 3.5 and about 7.5 to 8 inches down. And so again, in this one, there really is no compaction layer. What you can see on the bottom is that the red line pretty much parallels the gold line. The response is pretty quick behind it. If you get to that water treatment plant with this discontinuity, notice that first set of responses, almost nothing happens below the compaction layer. So effectively, it is acting like a resistance layer. It's acting like an impermeable layer until it gets wet enough, then it starts responding. So again, trying to understand what's going on, because this does impact how much water we can hold, is critically important. If you think about this as effectively, if anybody's ever gone to a barbecue, I'm going to use an old reference, but those old China paper plates, the first round when you go to a barbecue and get food, potato salad, whatever, get some of the sauce on it, they hold up pretty well, but the next time it gets a little gooey. And that's really what we think is happening with this soil compaction layer, is that it takes time for it to get wet and to soak through. And so you can think about it as your China plate as it's coming through. And then once it gets wet, it's really just going to go. So that's an important understanding. And then seeing how we can back that out into the modeling. So we have done that with this, and what we've come in and done is put in these sensors. And again, at this water treatment site, there's a downslope sensor. We have one on the embankment. This is our top and bottom sensors. And interestingly, if we look at this, again, blowing up on one of those storms, this is the bottom one you just saw on the vertical. The gold is the top one. There's the time delay from the time we see it at the top to the time we actually see it in the bottom. That's about 4 hours before we start seeing a response. Then the embankment and the blue one's down slope. Notice it never peaks as high and it never drops down as far. It takes a lot longer to drop down because it is at a slight angle, indicating that water is going at the shallow depth all the way down towards the creek. So we are getting horizontal water movement. Because again, those are above, except for the vertical bottom, all are above the compaction layer. So we get into SWIM, which is the stormwater management model, which is very commonly used in urban modeling. And we got 4 choices in here. We got the curve number, which Pennsylvania and Maryland like. We get green and amp, which is very theoretical based on Darcy's law. And then we get the Horton, which can be derived, but primarily is an empirical model. But most interestingly, what we notice, the only one that allows us to put in a maximum volume is Horton. Again, that's just the way the model is currently set up, and I'm having that discussion. But at least what it does, it allows me to say that's as much water as it can store. That's how much is in there. It's water storage. It is not going to be water plus soil. So you got to account for porosity. But none of these others do it. These others assume that once it's in the soil, it's going to at least slowly keep infiltrating until the end. So this is a challenge, but this obviously Horton doesn't allow us to think about it eventually passing water through. So there are some challenges in how this is set up. So part of this project is to look and see what's the best way to model these things. But again, as you get into the theoretical scientists, they would all love us to go to green and amped. Green amped, again, is a challenge. And again, some of the data that's in tables comes off of agricultural literature. And I can promise you that there are very few places in Baltimore or in Middletown that look like a farm field. So again, getting even some of these parameters is very difficult to try to translate them into the urban environment. So we actually came in with this. We actually modeled this, again, looking at this part of Middletown. And if I come in just to give you an idea, these are the inches are in water storage. So they'd be also modified by porosity. But just to give you an idea, 1 inch of water storage, normal porosity for a soil of that type, severe would be compacted or limited porosity. The April 2020 storm, we didn't get anything that flooded. This would be our current curve number system with climate. But what I really want to highlight is this July 2017 storm. That's the 4.71 inches in 85 minutes. And RSV simply is the ratio of runoff, is the fraction of rainfall becomes runoff. So it's runoff over rainfall. It's too late in the day, I can't talk. So what we see with this, again, down here is that if we have 1 inch, it doesn't matter if the soil is got high porosity or low porosity. We only have 1 inch of water storage. A lot of the rainfall is going to become runoff, and it just doesn't matter. If we were to have a little bit more storage, then the difference between normal porosity and restricted porosity is important, because with normal porosity, we can get more water in the soil faster. So less of that water runs off. So the idea is that we can begin to think about, where does porosity and compaction make a difference, and restrictive layer make a difference, because they really are interacting together. And that's what we're really trying to come back in and deal with. And what we did with that is turn around and take those results and then try to tie it back to the curve number, because that's what Maryland designs on, that's what Pennsylvania designs on. And it's just another proportionality constant between rainfall and runoff for those who haven't done it. And again, this was on our on one of our open sites. We would have predicted, if it was in good shape, we would have predicted it would have been in the 60s, again, in fair shape in the 70s, and nearly 80 here. But all of our models put it up closer to 85 to 100. So again, just based on the lookup tables in the model, that's not what we're seeing happen, telling us that we are getting way more runoff than we are predicting by any of the design models that are out there, which means more runoff means more pipe flow, which means more likelihood, if the pipes are not big enough, we're getting the flooding. So the other thing we're trying to do is develop equations that allow us to take this quick compaction measurements with this penetrometer, which takes about a minute to do at a site at each probe location, and try to see if we can relate that to the basically asymptotic infiltration rate, or Horton's F sub C. And surprisingly, it's holding up fairly well across several sites, but we're looking forward to seeing if we can expand it across into the Baltimore area and see if it's kind of hopefully it's not localized to that section of Pennsylvania, but it's much more regionalized. And if we can do that, even with this variability, if we can get our squares that are going to be about 0.75 with a significant regression coefficient, it gives us a place to start, so that you don't have to go out in the field and do a lot of heavy testing and a lot of mobilization of people, which the contractors don't want to do. We can actually get good measurements and estimates for those models, which will also help our regulatory community. So that kind of gives you an idea of what we're doing. Before I turn it over to James, with our urban soil conundrum, again, we want structurally sound soils for infrastructure, but we want water penetration, porosity away from the foundations of buildings and undercutting roads. And this is really a challenge in these very compact urban areas of Baltimore, of Middletown, and Philadelphia. Take your choice of these areas where we have very small lot sizes. So again, you saw a lot of the impacts of soil structure and infiltration. Again, we had lower infiltration rates and compaction, as we would expect, due to reduced porosity. But we're also very much likely to be underestimating the amount of flows that we're getting. So again, this is what we're working on. These urban systems really pose many challenges. We have varied streams, unmapped or incorrectly mapped infrastructure, development, redevelopment, rapid stormwater responses, and honestly, you don't know what's going to be in the ground when you go look at it. So it's one of those interesting challenges. And again, I'd just like to thank everybody who's put up money. And I do want to guess, for people who've not out there, you can go find the NPR story, because this really is coming down to the impact on the humans. And this is one of my neighbors a couple of blocks up the street. And this is the July 2017 storm. It got up to her first floor. She happens to live in a house that's at the bottom of the street. The street rises up on both sides of her. So effectively, she lives in the bowl. Now what she's really saying is she probably can't sell the house because nobody would want to buy it, because who wants that kind of damage? So she's really sitting there thinking that she's stuck with a house. This was not a tropical storm. This was just an afternoon thunderstorm. And we're seeing much more of those as time goes on. So with that, I'll turn it over to James, and then I think we'll take questions at the end.
Good afternoon, everybody. I'm James Hunter. Again, I'm an interim chair and associate professor in the Department of Civil and Environmental Engineering at Oregon State. And just following up on what Shirley had talked about, but I may take a little bit of a different direction and kind of give you an overview of how we look at some of the urban activities that we see in the city and what the impacts are. We know that this area in Baltimore is urbanized. We know what comes with that in terms of some of the social and economic issues, but there are some other environmental impacts, including air, water, and pollution. We see an increase in certain flooding events, but we can also connect the amount of development that we see in certain areas. The urban heat island issues regarding extreme heat. There are other things that come with being in these urbanized areas with traffic congestion, pollution, solid waste generation. So there are some evident areas of poverty, other issues that we deal with in urbanized areas with regards to unhealthy indoor and outdoor conditions. And really, we're talking about a loss of ecosystem services within the cities. So overall, we look at these impacts that a lot of times we'll be connecting to the abundance of impervious surfaces, but also connecting this to a lot of the issues that we see in the city with regards to human health and well-being impacts. We know that this development, urbanized development, has some real impacts with regards to not only water quality, which we'll spend some time on, but also looking at respiratory diseases and seeing that Baltimore has one of the highest rates of mortality when it comes to respiratory diseases. We also have a lot of other issues that come from the blighted properties and vacant areas that we have, and also exposure to different metals. When we look at land use change and urbanization, again, a lot of this is coming from impervious surfaces. And we're seeing increasingly more amounts or quantities of runoff and impacts to water quality. So a lot of times we're seeing impacts that are coming from various land uses. A lot of this is coming from what we call non-point source pollutants that come from various sources that are impacting our receiving bodies of water. And a lot of times we're looking historically at a city that's gone from no development at one point, something that's very urbanized. And we're getting increases in runoff. And what happens with that is we're impacting soils, right? So Shirley was pointing out that those impacts, at some point, we need to try and improve. Because if you see the layout of the city, we have a lot of development. So what you see in red is basically highly urbanized areas. You have some areas with some green spaces. But what do we do with these areas? And then how do we adapt these areas in the future? Particularly if part of our research here is to be looking at different ways to adapt the landscape and particularly look at the use of green infrastructure. So the issue at hand is that we have this abundance of impervious surface that's impacting how our land is able to infiltrate water. We know that disproportionately we have vulnerable and disadvantaged areas in the city that are at highest risk, particularly when we look at heat and flooding. The main way that we'll look at adapting these areas is by using green infrastructure or low impact development practices. And essentially, these are types of practices we want to integrate into the landscape to try and improve infiltration and control of stormwater. And these are the type of practices that we'll be looking at in terms of reducing some of those stormwater impacts. We have some other factors that are impacting the amount of stormwater that gets generated and how well it's being conveyed. We have a lot of aging and undersized infrastructure. We have, Shirley's pointing out, a number of piped urban streams that are on the ground. What do you do when now these systems are a bit undersized? A lot of these pipes were designed well over 100 years ago. Now we're looking at climate change and seeing some changes in the amount of precipitation in extreme storm. A lot of times we see flooding that happens because we have undersized culverts. So it's not enough capacity to convey that water. But we also have clogged, broken pipes and other channels. And then we also have some inconsistencies with how we design some of our practices. So this is a growing problem. And it becomes a big issue in terms of how we manage stormwater. And it also is a burden on not only the city of Baltimore, but all of our municipalities in the Chesapeake Bay. So there's a need for more investment to adapt to some of these changes. The other thing that we see is we also have some housekeeping issues within the city. And there are a lot of services that the city must invest in terms of operation and maintenance, not only with the gray infrastructure and cleaning out clogged inlets, but also maintaining a lot of the green infrastructure that we have. And what's pushing a lot of this is the regulatory environment that we have within the United States. So we're all about protecting the waters of the United States. There are MS4 permits that really have us to manage our stormwater systems. But you really have to connect this with all the services that are provided, not only at the federal level, but the state, local level, and also really integrating local stakeholders and nonprofits into this whole process. So it becomes a little bit more complex, and this is one of the drivers that we have for stormwater utilities. So this is pushing us to look at a number of different structural stormwater practices. A lot of these, again, when I talk to my classes, these are physical practices that we have to design, implement, and put into the ground. But we also have to recognize that these are systems that require a certain level of maintenance, particularly when you're depending on the green parts of these structural practices to work. It also means that we have to maintain and care for the soils that help to establish the vegetation. These systems often do a great job at filtering and trapping pollutants, but also containing and controlling some sort of volume of stormwater. A lot of this is green infrastructure, and a lot of times there's a whole paper on how do we define green infrastructure? Is it just the natural green infrastructure that's out there? As an engineer, I always go for those practices that we design that are meant to protect and restore and mimic some of the natural water cycle processes. A lot of times we'll see either anywhere from just planting trees or other vegetation or some sort of hybrid mix of green infrastructure that gets implemented. So when we look at the city of Baltimore and other areas in the state of Maryland, when we do new development or redevelopment, we're mandated to now include these practices within the landscape. We do that through something called environmental site design. So anytime you have any type of new development, redevelopment, particularly when we're trying to treat a certain amount of impervious surface, we must include these practices with the goal of treating the impervious surface with the goal of reducing associated pollutants from those surfaces. And that green infrastructure within an urban area can include all sorts of different practices. It can include, as I was saying before, trees, green walls, green roofs, urban green areas, parks, urban agriculture. And a lot of this is designed and can be strategized to handle stormwater and pollutants and trying to reduce some of the stormwater flows that we see that go or get conveyed into our stormwater systems. The green infrastructure in a lot of ways works as a patchwork of natural areas that get embedded into the urban area with the idea that we will be improving or reducing some of the stormwater impacts, reducing urban heat island effect, reducing energy use, particularly during the summertime, and also improving water quality, air quality, and um, providing some carbon capture. So when we think of the city of Baltimore, a lot of times we'll be thinking about our row homes. We have a lot of vacant properties. And so what this may allow us to do is really think about how we replace some of those vacant properties, redevelop these areas, and then embed different types of green infrastructure. Some of that may mean that we are remediating some of our soils and adding amendments. In other cases, we may be looking at different practices, which would include rain gardens or bioretention, bioswales that get embedded not only into private property, but what are the different practices that we can embed within the right of way. As Shirley had pointed out, there's a lot of stuff that goes in underground. Right? So this almost kind of creates a multi-objective problem for us to try and figure out where do we even put some of these practices, because you can't embed all of these different practices within the different landscapes. And again, adding green infrastructure doesn't mean that we're just adding practices that you kind of set it and forget it, but these are practices that often require maintenance and inspection. And we see this as part of the plan for different areas of the city. So here we have Broadway East, one of the neighborhoods that we're working with. They have their own greening plan where they're looking to expand the amount of green infrastructure. And essentially what this means is if we can get to this, we expect that there will be some reductions in stormwater associated non-point source pollutants. But we're also getting a lot of the co-benefits that come with having green infrastructure. The other thing we're looking to do in the city is to expand the city's tree canopy. So there was a study done a couple of years ago where the existing tree canopy was less than 30%. To be considered a healthy city, we're trying to move that to 40%. Tree canopy, expanding tree canopy is one of the best ways to kind of reap the benefits of what we get from green infrastructure, not only for the reduction of stormwater, but we also get all these other benefits with regards to improving air quality, storing carbon, reducing ozone, but also adding some aesthetic value to our neighborhoods. But when we expand those expanded tree canopy, we're getting these ecosystem services, but we're also creating some additional material that has to be handled. Now, one thing I'll point out is that as we look at a lot of these green infrastructure practices, some of them can also be considered as phytoremediation practices, right? So being able to put plants into a particular environment and being able to remediate or remove certain pollutants out of air, soil, and water. So again, these practices can allow these plants and these systems to be robust, they're solar powered, and they can be very effective at improving the urban landscapes. When we look at bioretention systems or bioswales, there are a lot of different processes that are happening. We're able to, in some cases, remediate some of the soils, put in certain vegetation that allows us to evapotranspirate precipitation, to infiltrate water, to allow for the absorption and absorption of different pollutants. These environments are also very active in terms of our ability to denitrify nitrogen and remove different nutrients out of the systems. So we know that these best management practices can do a great job at reducing the quantity of runoff and improving the quality of the runoff. But one of the things that we were looking at within our research group is how do you maintain and enhance the function of a lot of those BMPs, and really looking at the mix of sand, clay, silt, organic matter, and the type of plants that you need to put into those systems. The other thing is, how do you care for those soils in terms of maintaining soil moisture and really creating an environment that is providing optimal soil quality and also soil health. Had a student from industrial engineering who was really interested in trying to understand the reliability of some of these systems. Without proper maintenance, we sometimes see many failures of the green infrastructure that gets implemented, particularly in urban and ultra-urban areas. And sometimes those failures come from poor design or construction, poor maintenance, and often requires that these systems are monitored and maintained. These are just some examples of BMPs that end up not functioning so well. This is at Morgan State University. So if you have porous pavement systems or clogged drains, these systems don't necessarily function as well as they should. So there's a lot of work that goes into how do we properly maintain and keep these systems functioning so that they are providing the water quality and water quantity benefits. These are some additional systems that, as they mature over time, we tend to have some issues. Well, we tend to notice that Morgan State is we don't have the proper staff, or we have the staff that's not properly trained on how to maintain these practices. So this becomes very important as these systems mature. When they first get installed, a lot of times they look very, very nice. This is one of our bioretention cells. Now it's functioning more like a constructed wetland. And for some people, that means that system is now a failed system. The other thing we need to do is start looking at climate change and incorporating that into the stormwater design statements. And knowing that the design and build of infrastructure assets, we need to understand the precipitation conditions and the design standards. And they should reflect future precipitation projections and the operating conditions that we expect in the field. I had a doctoral student who went through Prince George's County and looked at nearly 60 bioretention and microbioretention systems. So these are installed green infrastructure. If you know anything about low impact development practices, the birthplace of a lot of this was in Prince George's County. So some of the oldest BMP systems were installed in Prince George's County, and some of these areas are also very much urban landscapes that these green infrastructure practices are functioning. What we were very interested in is looking at the soil health and soil quality of these systems. And what we wanted to try and see is there a connection with how well these systems function and how we can best maintain soil health and soil quality, and really looking at the living components of the soil, but also looking at the quality of the soil, looking at the physical aspects of this soil. So this work was finished just last semester. And what we were able to see is that if you look at the coverage of vegetation and also looking at soil respiration, we saw that when we looked at soil respiration, if those numbers were on the lower side, a lot of these systems that we inspected ended up there. As soil respiration improves, as soil respiration improves, we saw that more of these systems had a passing score. Right? So there's correlation between some of our soil health and soil quality parameters in terms of how these systems are performing. We also looked at the microbial population. So this also goes to how well those soils are functioning in terms of their compaction, their infiltration. But we also saw that the healthier those soils were in terms of the microbial population, more of those systems passed. And what we see is very poorly maintained systems really did not sustain any substantial plant growth. We also looked at infiltration rates. A lot of times the plants that get put into these systems, they're not wetland plants, they're not facultative plants, they're not able to survive if infiltration is very poor. So improved soil infiltration helped to spur on additional vegetation coverage within these systems. So that is for the green infrastructure practices, but there are also non-structural BMPs that we're concerned with. And what we see in the city is you get trash, you get leaf debris that tend to clog up our drains. With the trash, we know that there are some behavioral interventions and outreach that we can have with our communities. But we also know that there are some other non-structural BMPs that we need to concentrate on in terms of how we clean up or maintain the storm drain infrastructure. A lot of that comes from street sweeping and what we notice is that as we want to go and push this expansion of tree canopies in these neighborhoods, will that have an impact in how well some of this infrastructure may function? In the city of Baltimore, there are over 1,100 miles of storm drain pipes, 52,000 storm drain inlets, over 27,000 manholes, 1,700 outfalls throughout the city. So this is a lot of infrastructure, gray infrastructure that the city must take care of, particularly when we're shooting for adding additional green infrastructure, expanding the tree canopy. Why is this important? In terms of inlet cleaning, street sweeping, well, the city now gets credit for removing some of that material. So between trash and removing the leaves, they're getting credit for removing the nutrient loading that is associated with the leafy material. And so there's certain credit that is assessed, particularly around some of the housekeeping items in dealing with the O&M of this infrastructure. And a lot of this information gets reported back to the state. So again, we did a study with Center for Watershed Protection back in 2017, really looking at the inlet cleaning practices within the county. And so we look at this as source control. And for this one particular study, we really focused on inlet cleaning. And when you look at a storm inlet or a catch basin, there's a compartment that allows for that material to accumulate. And there's a capture of sediment and debris. And oftentimes this material needs to be cleaned out periodically. The type of material that does build up with sediment, leaves, trash that make up the majority of the material that gets removed. And so we look to, particularly for the city looks to maintain a lot of this infrastructure, keep the drains functioning, but also to reduce any unwanted effects in terms related to flooding that we see in the city. Now, we did this study again with the Center for Watershed Protection in cooperation with State Highway Administration. And these inlets get cleaned out a couple different ways, either with Vector trucks or they're manually cleaned out. And as you can see, in order to keep this infrastructure functioning, you get a lot. You have to really depend on the work and the service of these city and highway agency workers. So the study area that we looked at here was right within the city line, but also out towards the county. And there were a number of inlets that were sampled. This is part of the study that the Center for Watershed Protection worked on. Part of the study was us jumping into storm drains and cleaning out a lot of material. With the Vector trucks, they would come in and actually spray out a lot of that material, dump it. We would actually collect some of this and sort it in the laboratory. You get a lot of interesting material. You have a lot of the inlet structure, in some cases, actually falling apart. So a lot of them are like made out of bricks. Those brick pieces would be cleaned out of that inlet cleaning process. We did look at how that material accumulated, particularly in different land uses. When you had high density residential versus medium density residential, low density. And what you would see is different accumulations of different types of material based on those land uses. We also found some interesting items in these catch basins, which included strollers, a laptop at one point. As I was saying, sometimes the inlet structure itself is falling apart, which lets you know that we are dealing with aging infrastructure. And what we did see is within our residential areas, particularly as we go towards the fall and winter times, there is additional accumulation of debris, particularly related to the leafy tree material. And we want to be mindful of this, particularly when we start to look at flooding in certain areas, particularly our more socially vulnerable areas, because there are some additional housekeeping issues we have to deal with. There's a need for communicating to that, to the Department of Public Works and the other city agencies to make sure that these inlets are clean. Before there's a major storm, city would actually go out and tell people, please help us by cleaning out these drains. But this is something that should regularly be reported to the city in order to make sure that infrastructure is working correctly. So these are pictures that were taken by our undergraduate students as they were studying the flooding that was happening on North Fulton Avenue, which is near Mondawmin Mall. Near Morgan State University, on 35th and Helen. Again, we had one of those underground pipe streams called Tiffany Run. when we get these cloudburst events, it usually leads to some major flooding. So we had a bus that was underwater here, water that would go up to people's basements. This is something that's been happening for decades. That's a major frustration for the residents who live here. So we were finding newspaper articles that went back almost 30, 40 years. And this is also within that Helen Road area, 35th and Helen, where city firefighters are trying to clear those drains because, again, those drains get clogged and exacerbate some of the flooding that we see in this area. So what I leave you with is we are going to, within the BSEC effort, we're going to be looking at neighborhoods like Old Goucher and Broadway East, and really trying to understand as we expand the tree canopy, what are some of the operation and maintenance issues that we have to tend to. What we're going to be very interested in doing with this particular site is really looking at how those trees are growing with the other vegetation, some of the soil health parameters, looking at soil infiltration rates. They're doing some very interesting things to keep that vegetation going, particularly in urban and ultra urban areas. They're actually providing something called tree diapers that work near the roots of the plants. Tree diapers are essentially like these back materials with the same gel that is within diapers. That material swells up with water every time it rains and releases that water back into soil column. And we think that it's having a major impact on not only keeping the vegetation thriving, but keeping the soil very healthy in these areas. All right, and thank you. This is my son, a couple of years ago.
Do you want to start with questions at Penn State or start with the chat?
Let's hit the chat. I'm going to turn on our toss box, but what do we have in the chat?
So, Trista Bailey, do you want to just ask your question?
Sure. Yes. Thank you. I was curious if you were talking about, planting more trees in urban areas as good, stormwater management practice. But I've talked with other communities about their efforts to do that, and they've had some pushback from residents. I'm wondering if you've experienced any pushback from urban area residents, or really any residents, when planting trees is suggested, because if they're getting trees, that means they have to care for the tree, rake up the tree, pick up fallen branches, remove the tree if it gets sick. It could fall on their car. All kinds of things could happen. So even if you're given a tree, there's still a financial and physical burden potentially that could be raised. I'm just wondering if you've heard any pushback on that realm, and if so, how you've addressed it.
There is pushback in the city, and particularly certain neighborhoods. Not everybody wants a tree in their neighborhood, right? Even though we know innately what the benefits are for the trees. Some people don't want the trees because they had some unfortunate incident where a tree might have fallen on their car, or something's been damaged related to their own property. And there is a difference between a tree or other green infrastructure that is installed on somebody's private property versus that is installed within the right of way that should be properly maintained by the city. What often happens is trees and other vegetation gets planted, it's not maintained or watered or cared for. And then you end up losing that initial investment of what was ever put into the ground. So there is pushback. we've seen certain cases where a fire retention or stormwater pond was proposed. The city had gone through the whole design process, was ready to implement the project. And you have certain neighborhoods that really don't trust that the city will take care of that infrastructure. And that bringing in some sort of system that is holding water, they think will bring some nuisance, whether it be mosquitoes or rodents. And so those projects end up getting rejected by certain neighborhoods.
So we've seen it too, because the other end also has been sidewalk upheaval with trees. And, you know, and that whole idea of people having to fix the sidewalk just scares people. Is the cost.
Thomas? You want to ask
Yeah.
a question?
Sure, James, I guess I should step back and ask, is inlet dumping or catch basin dumping a problem? If it is, do you have any data to show a change in behavior when you label the inlets no dumping?
That is a very interesting question. That was something we attempted to do. We tried to do that on campus and around the area around campus. There is some proof that if you put some drain markers down, that it will deter some people from dumping. I don't know if we have like any. Let's study that really well. But it is one of the ways that communities are encouraged to discourage dumping, particularly with oil and grease that can go down the drains. But it also includes some vigilance with some folks in the community. I do believe that there is some reduction in some of the pollutant loading. I don't have a particular like efficiency that goes with that, but it is considered one of those education and outreach tools that are part of the MS4 process.
So where we've seen it has been more debris. So like not putting the leaves in front of that as in areas where people are seeing flooding. So again, my street, which is out of our flood area, everybody puts the leaves right on top of the grate. Yeah, I mean, because again, we don't have a problem. We got some hill to go down, but street down, everybody's out cleaning, so. I think Elliot's got his hand up and then it's Ken's real
Yeah.
one.
Let's give Elliot a shot and then we can see if there's any questions in the room here.
Thank you both for the talks. And this one's actually for Shirley. Yeah, especially when you're mentioning Middletown, where there's a lot of suburban areas. And I'm curious if there's a difference in soil compactness between, I guess, older suburban areas versus new developments.
That's an interesting question, Elliot, and okay, so Middletown in the borough itself has been developed between the late 1700s and about the 1950s for the bulk inside the borough itself.
Mm-hmm.
I would have thought we would have seen more recovery of soil capacity due to earthworms and other things that happened in some of the older areas, and we're not seeing that at least down to the compaction layer. We might be seeing a slight difference in the infiltration rates, but not enough to be substantially different. The work that I showed that came from Bob Pitt in the south, and maybe it's because fire ants are just much more effective, showed that about a recovery time of about 40 years, you actually get back to what are more native infiltration rates, but we're not seeing it where we are. We should have been in a position where we saw those. So that's actually one of the very interesting questions to be looking at up here, Elliot, is we're also coming into Baltimore and looking at Baltimore County areas to see how that correlates. I would have expected to see a difference that we haven't seen yet.
Interesting. Thank you.
Questions here? The box doesn't seem to be working, so I'll just carry the mic to you. Got a question here. Hang on just a sec. Whoop. Go ahead.
Can't pick a direction.
I actually had a question for James. When we were talking about, excuse me, we were talking about the cleaning of the stormwater inlets. Was that to reduce the risk of flooding from any clogging that's happening within those those stormwater inlets, or is that just limiting the amount of pollution that's resulting from those things?
It's really both, when considering what state highway administration is doing. When they up their activity in terms of street sweeping and inlet cleaning, a lot of that was to get more credit in terms of treating impervious surface. So that's where a lot of their motivation comes from, but the act of cleaning out those inlets is twofold. Is to maintain the capacity of those inlets, but also to remove any material. And they are getting credit for that from ND.
Do they get nutrient removal credit also for the removal of decaying leaves?
Yeah, that was the whole point of we needed to do that study for state highway, so they had
A credit number, okay.
credit number.
Not just for sediment or particles,
Right.
but also for, okay.
Hi, thank you both for the great talks. I was curious about how if a resident could improve the porousness of their lawn and sort of reduce the amount of compactedness, if there was any methods to do that.
So we're going to be looking at that as part of both the work in Pennsylvania and in Baltimore. There are tilling methods that you can do basically to go in and till or tear up the soil. So like the first residential site I showed, there was a spot in the garden where you could get down about 10 inches before you hit the compaction layer. And so, just garden tilling will do quite a bit. The biggest challenge is going to be knowing where that underground infrastructure is, knowing where your water line comes in or your sewer line goes out, which are probably low enough. But I'd be much more concerned if you've got any kind of wiring or gas lines that, we want to know how far down below, call before you dig type thing. So that's part of what we're really trying to take a look at and see, of course, and if you do have to be live in an area, there's more of a push to putting electricity underground. Then once we start getting electric wires underground, that's going to be add an additional challenge. So, yeah, there are things you could do that you can go to Home Depot or Lowe's or your local garden store and buy and do that. Also, you want to stay away from the foundation, just so you don't create leaks going in. Again, we're trying to think about having compacted soils where we don't want water and then having uncompacted soils where we would like it to infiltrate. So, some guidance says between around 10 feet away from the building. Others say you can go as close as 3 to 5 feet. We don't have a good answer on that one from the research, but hope to be able to take some of that out. Because these very small urban lots, you're not going to have 10 feet between two locations.
I had a question for you, Shirley. Keep
Sure.
you talking. Where did you get those turf grass numbers? Those are interesting.
Chesapeake Stormwater Network was one of them. And then the other one for the Pennsylvania was the Penn State Extension.
Excellent. Thank you. Good talk, both of you.
Thank you.
Any questions? Yeah, I see a hand in the room next to you, right, Darren?
Sorry.
Speak up.
I'm curious about something. You said you use the swing model, right?
Yes.
And you're looking for a better explanation for the input. Are you planning to use a hydrodynamical coupling model for the swing model to understand better the inflow? That might give you kind of a better understanding of how the different flows are functioning there.
We're looking into it. I don't have an answer fully for that because right now there are some good hydrodynamic models out there. We may more likely actually just be trying to couple the dynamic wave modeling and swim and PC swim into this. Because again, the second side of this is while BSEC is not a regulatory driven project, it's a DOE research project with a computing outreach component. There is a strong interest. The Bay Trust grant I do have is a regulatory project, and they want to know with models they're going to use what is happening. So we're trying to think of it both ways. There's a grade of getting into the theory or the high level modeling and then realizing that's not what your average consultant is going to do. So trying to balance those two. So, but we are working with people who are groundwater modelers, which is what I'm not. And again, thinking about how those models tie together and interact, particularly with the urban shallow subsurface environment that is poorly characterized and is incredibly heterogeneous, even if we could care, even if it was well characterized. So.
Yes, so I have a question.
Yes.
Thank you both for your talk. I was wondering, just throughout talking about all this, for like, you mentioned that large park areas and just like green space in general might also be compacted, like you mentioned, some failed bioremediation attempts. And for those large scale things like, say, a park, would the solution to uncompact soil still be tilling? Would we have to like?
Yeah, it would be.
Okay.
There is a researcher at the University of Maryland, Stu Schwartz, who's done a lot, for example, on ball fields at schools and others in parks. And he's looked at where you could get down there if you don't have the urban infrastructure. You could get down 2 feet. It'll almost behave like it is pre-development. What we're trying to figure out in our research is given these urban areas where we don't have 2 feet, what could be done if we could get a couple of inches? What do we gain if we could do 2 inches, 3 inches, 4 inches, 5 inches, 8 inches? That's kind of the balancing act because his research is really good. I just know, unless I'm in a park area that probably hasn't been developed, and so it doesn't have underground infrastructure. So it's not James's vacant lot where they tore down a house. It's going to be what truly has been a park for a long time. Is that how much can we think about then going down 2 feet, doing that kind of that mix.
But you can't go down 2 feet because there'll be infrastructure there.
Very likely.
But is the infrastructure everywhere over the side? Or?
No, it isn't. But what you're looking at is even if you, for example, had your sanitary sewer line, maybe even it's 4 or 5 feet down. If you keep infiltrating water into the soil, you're going to infiltrate water into it, which potentially, depending on how the valving is in the house, could have a backup into the house. And the last thing you've got is a resident who wants you putting more water into the soil, so it ends up in their basement. So, I mean, there's just a whole backflow and background issue. And if you've got any leakages, these older houses that have brick basements with grouting also potentially leak. I mean, so there's a lot of challenges in here that getting water into the soil to a point is really good. But in a small compacted lot could be a challenge. That's what we want to look at. Or also, you know, maybe in some places they didn't put it, it runs off the street where the right of way is. So the problem is the front yard, but not the backyard. So there's a lot of those things we're trying to, we're trying to figure out, but in places like Baltimore, particularly, or Philadelphia, others, Lancaster, near where I am, a lot of utilities actually ran down the back alley. And then the backyard's a problem. Maybe the front yard isn't, or the front yard may not exist because the house is so close to the road. So it's a very interesting challenge with that. So I see that anybody else in the room, but Thomas has his hand up otherwise.
Let's take the question from Thomas, then I'm going to dismiss the class gathered at Penn State at least. Keep talking.
Thank you, and thank you for your presentation. It's very informative. This is for Shirley, and I may have missed the point. You had mentioned difference in the penetrometers between wet and dry. And I think you might have mentioned that was due to porosity, but is it more due to the penetrometer having lubrication from the water? And also, when you get water within soils, it kind of floats the individual particles, so they're more easily pushed out of the way.
That's what we think is going on with if again, to get the deeper penetration when it's wet. Yeah, absolutely. It's just gonna move a lot easier. So that's exactly what we think is going on. Whether you would term it floating, again, more of you are soil scientists than I am. I'm an engineer, chemical by training. But effectively, yes, it's like lubricating it so that it'll go in a lot deeper, loosen it up a little bit. You know, again, it's not totally muddy, but it's definitely much wetter And shortly after a rainstorm, you can feel the saturation. So yes, and that's what we think is going on. But from a use standpoint, what it means is that's more water storage we have available. So it changes the modeling depth we would put in our model. So that's how I'd answer that. But hopefully I answered your question, Thomas.
Okay, thank you, sure.
All right, thank you again, Shirley and James. We're gonna call it an afternoon here in State College.
I'll go
Appreciate
park. I'll go find a parking space that on I-83 going north, Ken. Thanks.
All right, appreciate it. And folks, next week, Raman Azari, Wang Dazwo, and Jiajian Lin will be here. Actually, I'm not sure if Jiajian will be here, but two will be speaking here. Jiajian might be remote. We have yet to sort that one out. We will. Thanks a lot.
Thanks, Kate.
Enjoy your snow, Ken, and all of you in State College.
Bye-bye.